Okay, welcome to part 2 of the video on Introduction to the Op-Amp. As you'll recall, in part 1 we were doing the analysis of a voltage follower circuit and had gotten to the point where we had replaced the components of the op-amp we'd replaced the op-amp itself with an input resistance, an output resistance, and a voltage-controlled voltage source. And when we had done that, we had gotten the circuit diagram that's now in red on the screen. And so what we'd like to do is find the output voltage Vout in terms of our input voltage, 3 volts. And it looks like probably the easiest way to do this will be to use nodal analysis. So the first thing we need to do is define a reference node. We'll use the ground node that we used in setting up the circuit. We then have node 1, node 2, and node 3, and node 4. So we have 4 nodes here. Actually, this is a circuit that would also be fairly straightforward to do using mesh analysis. But since we started with nodal analysis, let's keep going. Okay, so if I look at node 1, we have that node voltage 1 is simply equal to 3 volts because we have the 3 volt supply connected to node 1. That was easy enough. Okay, let's look at node 2, okay, where we have V2. We have then that V2 minus V1 over 300 ohms plus V2 minus V3 over 1K ohm is equal to 0. Okay, and we can then simplify this as minus V1 1 over 300 ohms plus V2 1 over 300 ohms plus 1 over 1K ohm minus V3 times 1 over 1K ohm is equal to 0. Okay, so that's our second equation. Our third equation we'll get at node 3. So let's see, we'll get V3. Okay. And at node 3, we will have, let's see, we'll have V3 minus V2 over 1K ohm plus V3 minus V4 over over 50 ohms plus V3 over 1K ohm, and that will be equal to 0. Okay, so we can simplify this a little bit to say then minus V2 over 1K ohm plus V3 1 over 1K ohm plus 1 over 50 ohms plus 1 over 1K ohm minus V4 times 1 over 50 ohms. And this is equal to 0. Okay, so that's the equation we get from node 3. I'll clean up just a little bit, although we won't really need much more space. Node 4, you'll notice, is connected to this controlled source. So V4, we have V4 will be equal to 10 times V plus minus V minus. Okay, but we know that V plus minus V minus, that is, this voltage across this 1 k ohm resistor, is equal to V2 minus V3. So we have V4 is 10 times V2 minus V3. Okay, so now we have 4 equations and 4 unknowns. Once we solve these, we should be able to tell what the output voltage Vout is, which turns out to be the same as V3. So let me write this down so we can solve it. Okay, we have then V2. My wife just got home. She's singing in the background. I'm sure you can all hear her and appreciate her melodious voice. Okay, so these are our equations that I've just written down. And we'll go and solve them now. So we have V1 is equal to 3 minus V1 times 1 over 300 plus V2 times 1 over 300 plus 1 over 1000 minus V3 times 1 over 1000, and this is equal to 0, minus V2, 1 over 1000, plus V3, 1 over 1000, plus 1 over 50, plus 1 over 1000, minus V4 times 1 over 50 equals 0. And finally, V4 is equal to 10 times V2 minus V3. And we tell Wolfram Alpha to solve that. And it gives us the following numbers. We have V1 is 3, which is what we would expect, because our source pegs it at 3. V2 is 2.92. V3 is 2.64. And V4 is 2.76. So let's go back to our circuit and see what this tells us. So we had V1 was 3, which we expected. V2 was 2.92 volts. V3, which is also Vout, is 2.64 volts. And V4, which is the output of our source, was 2.76 volts. Okay. Well, so we had to resort to nodal analysis to do this, to solve it. It was some work. We discovered that the output is reasonably close to 3 volts. And I'll leave this as an exercise to the interested reader. I'm not going to redo this. But as we increase the input resistance, which is 1 k ohm, and as we increase the gain, so we change the input resistance from 1 k ohm to 1 megohm, for example, and increase the gain to 10,000, then this output voltage would get very, very close to 3 volts. Okay, so for a real op-amp, again, this output voltage would be very close to 3 volts. And again, if you want to, you can go and make these changes in the computations and verify that what I'm saying is true, just in case you don't trust me not to lie to you. Okay, so if we go back, whoops, we seem to have destroyed our voltage follower circuit. So what we'll do is clean this up and redraw our voltage follower. We had 3 volts and 300 ohms. This goes into the non-inverting input. The inverting input is connected to the output, and this is connected to, if I remember correctly, a 1K ohm load, and we want to find this output voltage. Okay, so let's go back to our ideal model, which basically says that the input resistance between the inverting and the non-inverting inputs is infinite. That has an interesting implication. What that says is that the current going into the non-inverting input is 0. The current going into the inverting input is 0. No current flows in the inverting or the non-inverting inputs. Okay, and the other thing that that we said about the ideal op-amp model is that this output, the output of the op-amp, right here, that's the output of the op-amp, will be whatever it needs to be to make the difference between the non-inverting and the inverting input 0. Okay? Because if you assume the gain is infinite, the only way you can have the voltage out here at the output be something reasonable is if the difference between the two inputs is 0. So in other words, this voltage at this point will do whatever it has to make this voltage and this voltage the same. Okay, well, let's see what V plus is, what this voltage at this point is. I have 0 amps flowing through this resistor because there's no place for the current to flow. If I have 0 amps flowing into the op-amp, then there's 0 amps flowing through the resistor, which means that the voltage across it is also 0 volts, which means that V plus, the voltage from here to my ground, V plus is going to be 3 volts. It's the same as this source. Okay. So now I also have that my op-amp is going to make the output here be whatever it needs to be to make V minus equal to V plus. Well, V plus is 3 volts. That means that V minus will have to be 3 volts. Okay. So this point here is going to be at 3 volts. But you'll notice that this point here is all part of this same node. Okay, because I fed the output back to the inverting input. So what that says is that the voltage V out is going to be 3 volts. Okay, and again, that's because the output voltage will be whatever it needs to be to make V minus the same as V plus. So what we have here is a circuit whose output is the same, the output voltage is the same as the input. Some of you might think, well, why don't we just replace it with a wire? Well, it turns out that it has useful properties in the sense that it decouples the input side from the output side. So it's actually, in spite of the fact that it looks kind of weird, it's a useful circuit. So this ends our introduction to the op-amp. Hopefully you've found this useful. The important points to remember is that, well, how op-amps work, and that the ideal model, the model where we assume that the V plus is equal to V minus and no current flows into the inputs, actually makes our analysis quite a bit easier. You can see that we did this one very easily, where the previous one we had to use nodal analysis and it took a while. So hopefully you found this useful, and we'll quit at that point.